This is Algebra 1, Lesson 5.5. I uploaded one without sound, so that one is wrong. And this lesson starts on page 298 in your books. And this lesson is modeling with linear equations. And linear modeling, linear regression, as you'll study a little bit later in high school or college, is really exciting because every area of business in the world or study, academic study, uses linear modeling to predict or forecast what's going to happen. You can use it, as we'll see, lots of different ways in life, but this is one of the coolest parts of Algebra 1, I think, because it's used every day, every kind of business. Here's an example of linear modeling that shows the change in Oregon Latino population, age 18 to 34 through 1990 to 2010, and it charts by age, which is the red line, and it charts the number of Latinos in the blue line. But linear modeling is a linear function that is used to model a real-life situation. So this is about real things that happen, and it uses a rate of change to compare two quantities. In this case, the number of people that are a particular age versus the number of the amount of population for Latinos in Oregon, and it shows you a slope, what the trend is, and you can predict. So this went through 2010. But they could figure out then, based on this linear modeling, what they would predict for the next year and the next year or 10 years out. And granted, it could change because something might happen, but it gives you real life predictions that you can use. If a school needs, let's say Cheney, Goddard wants to figure out, is it going to need a new building in 10 years? It has to use this to chart. Could you predict how many people might be moving into the district? They could take birth rates and predict, 10 years down the road, how many kids will we have in a certain grade, to know whether or not to do a bond issue and raise money and to do new buildings. So this is very important to real life. I have a cough drop in my mouth and my battery's about to go dead, so I'm plugged in and working on this to get sound since I did it wrong. Very cockeyed, so I'll try to make this make sense. We want to write a linear model. From 1985 through 1997, we know that the number of movie theaters in the United States were increasing about 750 per year. In 1993, there were 26,000 theaters. So if you were asked to write a linear model for the number of theaters, you would use Y, and think of Y as X, but we use Y. And we're going to let T, and I'll tell you, you'll see what T means in a minute, T to equals 0. I think I said that wrong. The number of theaters is Y. We know that. Think of T as X. I'm sorry. So let T equals 0 represent 1985. So in 1985, we would have, we're going to start with 0 as that. So how we write a linear model is, we already know the information which I highlighted up here. We had a rate of increase which was 750 per year. That's the slope. The increase is the slope there. The year 1993 is going to be represented as T equals 8 because that is 8 years after 1985, and we were using 0 to represent 1985. So we add 8 years to that to get to 1993. So we're going to use the point slope form because we have, and that is the y minus y1 equals m times t minus t1. And now we're going to substitute in, and again, we've got the information here. We're just putting this into a linear form here. So we substitute 750 for the m. So that's right there. We substitute the 8 right here for the t1. And we substitute 26,000 for the Y1, and we put that right there because that was the information we had in 1993. That's 8 years past 1985. And this is a little confusing when you look at it because you have a Y and you have a T, and we're leaving those alone. We're looking at the Y1 and T1, and we're plugging in these numbers. So now we use the distributive property and we distribute everything. So we multiply out the 750 times T is 750T. 750 times negative 8 is negative 6,500. And then on this side we still have that nothing changes. Now we're going to add 26,000 to each side to isolate the Y. So we end up with Y equals 750T plus 20,000 because we had to subtract the negative 6,500 from the 26,000. Somehow that doesn't work out there. Okay, that's why, because this is a 0 and a 0. Okay, that's 6,000, not 6,500. I do want to make a note that this is example 1 on page 298. Let me just write that down. This is example 1 on, that doesn't look like a 1, does it? Example 1 on 298. And so you can, if you need to refer back to it or you get confused moving back through the slides, you can go back to that. Space, I ran out of space here, so I rewrote the formula. So our linear model is right here. It's Y equals 750T plus 20,000. Now I will explain how we use this information, but this is the model here. Just know that the format is Y equals 750T plus 20,000. So the linear model for the number of theaters in the United States is Y equals 750T plus 2,000. Knowing that, now that we have the model, we can plug in numbers and figure things out. So that's why you figure out the model first, and then you can figure out, you can input data into there. Again, statisticians use computers and can input lots of data and pump out lots of numbers. But again, we did this where the T was 0 to represent 1985, which was the first year that they had the data. So
I ordered the soup. Of course, my apologies. Come on, Caesar. Let's go.
So let's go a little bit further here. From 1985 through 1997, movie attendance in the United States was increasing by 25 million per year. In 1994, the movie attendance was about 1,300 million. So now we need to write a linear model for the movie attendance that will use Y, and that's going to be in the millions. And we're going to let T equals 0 represent 1985. So you should get a pattern here. The first year that we're using with our data, we're using that as 0. And we have one known point that it's given us. We know that in 1994, that's 9 years after 1985, that the attendance was 1,300 million. So that's my data point. It's 9 years later. It's 1,300. And I don't know why I have this right here written, so I'm just going to eliminate it. This one is checkpoint, and it's number 1 on page 298, so you can refer back to it if my notes are too messy here. Now it told us that the slope was equals rate, and that was 25 million. It told us we're going to use the point slope form, so that's y minus y1 equals m times x minus x1. I plug in my numbers. I have the y doesn't change. The 1,300 is the 1994 attendance that I just that represents 1,300 million. equals 25. M is the slope. And x minus 9, and 9, and the 9 represents, hang on, 9 years from, oh, I lost my train of thought, from 1994 minus 1985. So that's where the 9 comes from. 25 is the rate there. So I work this out here, distribute it through, and I end up with y minus 1300 equals 25x minus 225. And now I need to finish it with y equals and I needed to get rid of my 1300 there, so I would have 1300, that was a negative, that will be minus, got on eraser, 1075 after I subtract 1300 from both sides, or add 1300 to both sides, sorry. And then y, my model is y equals 25x minus 1075. So what I've done here is figure out my model, and now I can use that information and go one step farther. So you have to get the model first, the formula, to figure out, to do the next step. So our formula is going to be y equals 25t plus 1075, where t equals 0, representing 1985, and y is going to be in the millions. And I just added a little graphic here because even so that you just understand that we're still talking about our coordinates here. And we would say y equals 25t plus 1075, where t equals 0, representing 1985. Y was in the millions, and it was increasing at 25 million. This just shows you that we could use this information now to plot a line, a prediction line, and using the same coordinates that we've been working with, x and y. Now, the cool things that you can do with linear modeling, and like I said later, using linear regression and stuff, is you can predict life expectancy, how long people will live, or people in a certain state will live, how long men will live. You can predict the number of voters that might show up in an election, which voters might vote for Trump over Clinton, perhaps. You can use linear modeling to figure out the cost of repairs and maintenance over a 5-year period of your car or a bicycle. You can figure out salary increases or how much profit a company will make over a period of time. You can use it to predict sales and sales income. You can use it to predict expenses, loan payment costs, or what your loan will be if interest and stuff is adding on. The travel rate, how quickly it would take you to climb a mountain, or attendance, how many people will attend or go to movie theaters, or how many people will be in attendance at school. Everything in life can be, you can use a linear model for almost. So now we're going to use our linear models that we just figured out to predict. And so we've worked through 2 samples. We had the number of how many new theaters were being built each year between a certain period. Again, we're looking back on data, but we're also going to use it then to figure out, based on that data, what would it be in 2017. And we can also look at the number of people that were attending during a certain period, and then use that data to figure out what it will be in 2017. And we can also, we're going to use 2 methods with this information. We're going to use an algebraic approach and write the linear model and then use it to plug in information, and then we're going to use a graphical approach and put it on a graph and plot our points. And one of the first thing that we're going to look at, which was from, I think, slide 3 and 4, is the number of movie theaters. And our formula that we used was we had y equals 750t plus 20,000. Now we're going to be talking about what we figured out for example 1 on 298 for this here. Okay, and then this example 1 from 298, it carries on and does its becomes example 2 on page 299. So this is working the same problem. We got the linear equation. We got it for 2 different examples for the number of theaters and attendance, and then it takes it one step farther to take each of those examples and predict. So if this gets confusing, I'm sorry. So using the algebra. Okay, and this is working with, this is using the linear model to predict. This is example 2 on 299 if you need to refer back to it. It's example 2. And we're going to use the algebraic approach to, and t equals 0 represents the year 1985. 2005 is represented by t equals 20. We're going to write the linear model here, which is y equals 750. That doesn't really look like a 7. Let me see if I can get that to... Nope. See, it won't write where I want it to. Okay. Well, I give up. You'll just have to go with that's a 7. For some reason, my stylus won't let me correct it. Y equals 750t plus 20,000. We're going to substitute 20 for t because that's the number of years. We have y equals 750 times 20 plus 20,000. And then we distribute that out, and we end up with 35,000 here as the answer. Y equals 35,000 for the year 2005. And our answer is you can predict that there will be about 35,000 theaters in 2005. So how would you figure out how many would be in 2017? You need to solve this. This is as part of your homework. And again, this is example 2 on 299. I just want to say again, because I added that on at the end of that, and you may have already paused it, is that these things that I'm asking you to solve, there's a couple of them in this lesson. So if we look at the graphical approach to the equation that we've been working with, we're going to graph this equation, y equals 750t plus 20,000. We remember that the t when we started with the first year was 0. So we have 0 and 20,000 is our first point on the graph. And on the bottom is the years since 1985. Let me write that. This is years since 1985. And over here on the Y is attendance. Oh my, I didn't even. And so Y here is attendance, and over here the X is years since 1985. And then we have, and we know over here that the second point is going to be 20 years, because that's the difference between the two dates. And when we worked out this equation, we ended up with 35,000. That was the equal sign there, so that's that. And then if you extrapolate that out to 2017, you're going to end up with a point of 32 years since the start, and something like 44,000. So you can check and see if when you solved it earlier, did you have that same answer? And you can see here we can predict. We could keep going. We could predict for 2020 even. Now that we have this formula, all we got to do is plug in the year, how many years it's been since 1985. I just realized that I said this one wrong. This is not attendance. This is the number of, just a second. This is the number of theaters. I confused this chart with another. This is number of theaters here. That's what that stands for. So then how would you use this, display this graphically? And so, again, our equation is 750T plus 20,000. T, we're going to put in the number of theaters for that year. I mean, that year that we're talking about, how many years. And you can see how I graphed this. So our first point was 0, T equals 0. And it was 20,000, so that goes right there. We then figured out, hopefully you got this, that it was 20 years later, and that equals 35,000, which is what I just did on the slide before this. We had here the number of theaters in here, and then here, I first had written the wrong thing. It's number of theaters, and then the years since 1985 here. And you could, this line, which isn't very straight, because I can't do straight lines on here, but we could predict out to 2020 or 2030. Now on slide 5 we talked about movie attendance in the U.S. from 1985 to 1997. In the year 1994, you remember, even though this writing is horrible, it's the very best I could get this stylus to do. Movie attendance was at 1,300 million. We had T equals 0 for 1985. And now we're going to predict for 2005. So again, we're going to let T equals 0 for 1985, meaning that for every year after that, that T will change. We're going to use the algebraic approach. We'll subtract 1985 from 2005. That's 20 years. And then we have our model that we figured out on slide 5, where it's talking about the movie theaters. And that is y equals 25 times 20. That's T is 20, because that's how many years, plus 1,075, which is what we figured out in that example as. So I work out this formula, y equals 25 times 20 plus 1,075. Looks like a 2, but it's a 7. And we find out that y equals 1,575 million. Now, how would you solve this for 2017? You've got to figure out the difference between 1985 and 2017. So stop, figure that out. You're going to turn this in. This is your assignment for today. And just to note that I referenced slide 5, but this is checkpoint number 1 on the bottom of 298. Now we're going to go back and refer to checkpoint number 1, which was on 298, with the example about the movie theaters. And in that one, movie attendance. And in that one, I think that's about slide 5. Movie attendance in the U.S. from 1985 to 1997 is what we're talking about. It gave us the information that in the year 1994, movie attendance was 1,300 million. We had T equals 0 for 1985. Now we want to predict for 2005. It's going to be the exact same thing we did for example 2. We're going to follow the exact same step-by-step approach. We're going to let T equals 0 for 1985. Doing the algebraic approach, we know that 2005 minus 1985 equals 20 years. We have our linear model, which we did the first time through. So this is connecting back to what we did. And that was y equals 25t plus 1,075. We were given the slope rate of 25 million. That's why we know that 25 goes there. We plug in the years, we work that out, and it is 1,575 million. Now, how would you solve this for 2017? Again, you got to figure out the years difference and then plug in the numbers. And then we could graphically represent this with the same formula, y equals 25t plus 1,075. And over here we have so we're back to, and then how would you display this graphically? we have the same equation, y equals 25t plus 1075. We know the slope is 25. So our first coordinate, because t equals 0 here, is 0 and 1075. And then we know that in 20 years, we have 20 as that point, and 1,575, which I just put at 1,600 because it was almost that. This side over here is representing the number of theaters, or number of the attendance, and over here is the number of years since 1985. This, and now you need to graph it for 2017 as part of your homework. Now let's say you want to use this for real life in something that you might have to do, something maybe they might even have done for the dinner theater, figuring out the food. Let's say you're buying hamburger and chicken for a barbecue, or like I said, it could be a dinner theater. The hamburger costs $3 per pound and the chicken costs $4 per pound, and you have $60 to spend. So write an equation to model the different amounts in pounds of hamburger and chicken you can buy. And we're going to use the model to complete a table that will illustrate the different combinations and predict for us. This is example 3 on page 300. So our solution would be is to figure out the verbal model. We have the price of hamburger, the weight of hamburger. That would be the price of hamburger times the weight of the hamburger, plus the price of chicken times the weight of chicken equals the total cost. When we label this, we're going to know that we're going to use 3 as the price of hamburger per pound. X is going to represent the weight. The price of chicken per pound is, we're going to use $4. And we're going to use Y for the weight, and the total cost will be $60. Our algebraic model will be 3x plus 4y equals 60. And we can plug in our amounts once we figure it out. So let's look. I have it figured out here. I want to show you how to do it. If we have 0 pounds of hamburger, then we have our formula here. We have 0 hamburger. We put that as x. So we have 3 times 0 plus 4y. That's that equals 60. We end up with 3 times 0 is 0, so we have 4y equals 60. We divide both sides by 4, and y is 15, and we put y as the pounds of chicken, and that goes there. So if we buy 0 pounds of hamburger, we can buy 15 pounds of chicken. The next one, we know that the hamburger, it disappeared, $4. So with the blue one here, we know the hamburger is 4 pounds. So that's $3 times 4 pounds plus 4y. So we can figure out how much chicken we can buy. We work that out. That's 12 plus 4y equals 60. Subtract 12 from both sides, and that's going to be 4y equals 48. We divide both sides by 4 to get rid of the 4. And we end up with y equals 12, and that is that one. And then I worked out the rest of these. You need to work out the rest of these. I give you the answer 9630, but you need to make sure that you can do that and you understand why 963 and 0 is there. So you can show that on your piece of paper for me. $4 because it. Oh, sorry. And then using the points that we have. Hamburger at 0, and I can buy 15 pounds of chicken. I could plot that. I could plot 4 pounds of hamburger will give me 12 pounds of chicken. I can plot 8 pounds of hamburger and 9 pounds of chicken. And by the time I plot everything out, I have a nice line. Your assignment is to do solve all the pieces that I told you to do in this lesson, and then to do checkpoint on page 300. It would be checkpoint 4 on page 300, and it's going to be doing the same thing except using pasta salad and potato salad instead of hamburger and chicken meat. And that is it for today. So you can shout, you can jump. That's all today. So isn't that a yay?